Hello, today we're going to be looking at a incline plane situation or a ramp. And of course, you remember it all depends on how we draw the ramp, how we set these up, but it won't make any difference. We'll still be able to get the answers that we're looking for. So if you watch the grade 11 videos, you know that I go through with the highlighter. I didn't do this in class, but I think I might start. So a 100 kilogram box is pushed up a ramp with an acceleration of 1 meter per second squared. How much force is being applied if the ramp makes an angle of 10 degrees and the coefficient of friction is 0.3? Would the box slide down on its own, and would it be harder to push up the ramp if the angle is 30 degrees? So I've got a 100 kg box. I've got an acceleration of 1 meter per second squared, angle of 10 degrees, and coefficient of friction is 0.3, and I want to know the amount of force. All right, let's take a look at this. I always like to draw the ramps. I have a preference for this direction myself. I think it's this way that I can then figure out acceleration. Less mistakes I find this way. That's up to you though. If you like to draw it the other way, that's totally fine. So there's a box sitting on the ramp, and if I draw my forces on it, the only two real forces are, shouldn't say only two, the only real forces are weight, and we're applying a force up the ramp. So there's an FA, there's friction, and then there's the normal force. Those are the forces that are acting on it. Of course, you remember also there's a parallel force, right? So we need to figure that out. But these are the only actual forces. And we want to figure out, and of course, an F net equation, and then figure out our FA from there. Now we do remember that weight is broken into two parts, part of which makes the object go down the ramp, and we call F parallel, and part of it which goes perpendicular to the ramp, which we call F perpendicular. Now remember, if you take this in future classes, this is going to be Fx and Fy, because they take the whole thing and turn it flat, where the surface is your coordinate system, and that is flat. But we don't do that. I like this way better. It seems to make more sense to me, but be ready to be adaptive if you have to. So let's look at F net equation, and we say that this is the direction we're going. So this is the positive direction going up the ramp. So F net equals all the forces that are pointing up the ramp, which is the applied force, minus any forces that are going down the ramp. So friction and the parallel force, and they both go down the ramp. And you remember, we don't have a whole lot of formulas in this section because there's not a lot of actual formulas. These are all created from the diagram. So we're going to do some replacement here. So F net, of course, is MA. We know that. FA, we know, is just FA. It's an actual measured force from applying something. Friction is mu times the normal force. And F parallel is the component of the weight that goes down the ramp. And if you can't remember, we use F parallel because we don't want to mix it up with X. So it's going to be the weight times the sine of the angle. So we're partially through our changes here. Now we should look for the normal force. In this case, the normal force is equal to F perpendicular. And of course, F perpendicular is that component of weight that acts into the surface, which is W cos theta. So we're going to substitute that up here. So the next line, MA equal to FA minus mu, and the normal force we said was W cos theta, and the parallel force is W sine theta. And one more line. You don't have to throw all these, depends on your memory. Get the applied force minus mu, weight is mass times gravity, times the cos of the angle, minus mg sine of the angle. So you don't really need this line right here. I'm just kind of reiterating where it came from, or even in fact this line, if you can remember how they came. You just need this one. Now we're at the point where we can substitute in. Can we cancel out the mass? No, because the applied force is here. If there was no applied force, then the mass is irrelevant, but we need the mass in this one. So let's put our numbers in. So we've got 100 times the acceleration of 1. The applied force, we don't know, that's what we're looking for. Mu is 0.3. Mass is 100. Gravity's 9.8. And we're doing cos of 10 degrees minus 100 times 9.8 times the sine of 10 degrees. So that's 100 right here. This is the applied force. This value is So I'm going to put these numbers in my calculator. You can do it all in one step, but I have a point I'm going to show you. So I'm going to put these in a couple steps. So this number right here is, if I've done my calculations correctly, 289.53. And this number right here, that should have been a 10 over here, not theta. And this number over here gives me a value of 170.18. Of course, I want to move these to the other side, so I put them on the other side, and I should get a value of 559.71 newtons is my applied force. But think about it, that's almost 300, 470, and I want to accelerate it, so 570, 560, so that works out about right. Okay, so that is our applied force. Part B said, would the box slide down on its own? Well, let's just look at this. This value here is the force of friction, and this value is the applied force. Or sorry, the parallel force. The parallel force needs to be bigger than the force of friction in order for it to move on its own. So the answer to the part B is no, because the parallel force is not greater than the force of friction. Part C, would it be harder to push it up the ramp if the angle was 30 degrees? So I put 30 degrees in here. The bigger the number gets for cos, the smaller this value gets. So as at 30 degrees, the force of friction is going to decrease because less of it, the force is in the x direction, and the parallel force, because the sine, as you know, sine of 0 is 0 and sine of 90 is 1. So the closer this gets to 90 degrees, the greater that's going to get. So as this goes greater, we're going to have to apply even greater force to overcome the parallel force. The friction will decrease, but the parallel force will increase at a greater rate. So the answer to part C would be, yes, it'd be harder to push the box up a ramp. All right, folks, thanks for listening. I'm just going to drag over the solution here. I wrote it out ahead of time. I'm just going to erase what's here so you can read the solution if you want. If you got any questions, there's the answer. Applied force 559.71. Look at the numbers. Friction is greater than the parallel force. So it won't move, and it is harder as the angle increases, the value of sine increases, and cos decreases. And of course, we have the coefficient of friction here. Thinking logically, it's easier to push up on a level surface than it is on a steep one. So that's where this comes into play. The steeper it gets, the harder it gets. All right. Thanks for listening. If you have any questions, feel free to email me or drop in and see me. And I hope to see you again. Thanks.